Welcome everybody to today's joint Heidelberg Astronomical Colloquium. It's the penultimate in this semester's series, and as you've realized, a running theme has been the use of precision astronomical observations to address questions in fundamental physics. And we're very honored and pleased to welcome Ryan Cooke from Durham University here today, who will continue this theme as one of the current leading proponents in the field of optical spectroscopic observations of element abundances and other things. And I hand over to his host, Diederik Christian, to give the formal introduction.
Thank you, Richard. And yes, thank you very much, Ryan, for joining us today. It's been a long time coming, and I'm really glad it worked out this semester. It's fantastic to have you here. For everyone else, Ryan is a world-leading expert in Big Bang nucleosynthesis and primordial abundances, also in studies of the first stars and damped Lyman alpha systems. He's been working on that with fantastic work over the past decade or so. And in 2011, Ryan received his PhD from Cambridge University, where he worked with Max Bettini. He spent a year there as a postdoctoral Peterhouse Fellow. And then in 2012, he moved to Santa Cruz, where he first was a Morrison Fellow and then later a Hubble Fellow. And since 2016, he is now a Royal Society University Research Fellow and a lecturer at Durham University. And I expect that he will be telling us about the activities of him and his group at Durham in his talk, The Genesis of the First Elements, today. So Ryan, thank you again, and please start when you're ready.
Great. Thanks very much, Diederik. Just to check that you can hear me okay?
Yep.
Very good. So thank you very much for the really lovely introduction. I wasn't expecting such kind words, but I really appreciate that, Diederik. So third time lucky. We've tried to organize this colloquium 3 times now, so I'm really grateful that you've given me this third opportunity to schedule this talk. Today I'm going to talk about the genesis of the first elements. And by this, I mean 2 periods of time in the universe where the first elements were made. I'm going to roughly split it into 2 sections. So the first elements that were made a few minutes after the Big Bang, and the first elements that were made by the first stars in the universe. I encourage you to interrupt with any clarification questions during the talk, but I won't be checking the raise hand button, so feel free to interject as you wish. So to get started, I wanted to first give everyone a sort of sense of the timelines that are important for this talk, but also some of the most important events that happened in our universe. So I'm going to start on the top right, where you see this sort of fireball picture. This is representing a few minutes after the Big Bang, when the universe was hot and dense. And during this time, a few minutes after the Big Bang, the universe was in just the right conditions, had just the right density and just the right temperature that the first elements could be made, predominantly hydrogen and helium. Then after this short period of nucleosynthesis, when these hydrogen and helium nuclei were made, the universe became fairly boring and did nothing much. And we can't probe that at the moment. The latest times that we can probe with photons is the cosmic microwave background, which is shown by this image in the top and the middle. And this is when photons decoupled from baryons. And we can see this as temperature fluctuations imprinted on the cosmic microwave background. And we can use this to study cosmology in a great amount of detail. Now, after photons decoupled, the universe again became pretty boring, and we haven't got many tools that we can probe this part of the universe. But something very important was happening during this time, and that is that gas and dark matter were being funneled down filaments. And it's when at the intersection of these filaments, that's where the first bound structures formed in the universe. This is where gravitational force was the strongest at these times. And it's at these regions that the first bound structures formed. And inside these structures, the first stars formed. Now, the first stars were formed out of the material that was left over from the Big Bang. So the ashes of the Big Bang have gone into making the first stars. And because that primarily consisted of just hydrogen and helium, the first stars were believed to not be very low mass. So the first stars are currently believed to be relatively high mass because we didn't have sufficient cooling agents in order to fragment down to low mass scales to form low mass stars. Okay, so the first stars formed, they're predominantly very massive. And because they're massive, they live short lives. Massive stars live short lives. And so we haven't yet found a first star, a pure metal-free star to date. But this is an ongoing goal of many missions. In particular, the James Webb Space Telescope is hoping to detect some of the signatures of these first stars directly. One of the signatures...
Sorry to interrupt. What is the redshift, typical redshift you would expect these first stars to be formed first?
Great, thanks for the question. Yes, so the typical redshift you expect the stars to form will be less than redshift 30, but probably higher than redshift 15. So we're talking about redshifts 15 to 30 for the dominant population, but some will still form after redshift 15. Okay, so because those first stars were very massive, we believe they would have ended their lives as a supernova explosion. And this supernova explosion would have not only heated the surrounding gas and the surrounding medium, but it would have also enriched that gas with its first dosage of heavy elements. Eventually, that gas will cool and condense to form some cloud of gas. And this cloud of gas will then become neutral and form the second generation of stars, which is what you can see on the bottom right of this slide here. Now, because we're now using those metals from the first stars and from the first supernovae, we have the carbon, oxygen, and iron that allows us to form a low mass generation of stars, which is what we can detect in the Milky Way and in low mass dwarf galaxies today. So just to summarize, today I'm going to talk about the hydrogen, helium, and lithium that was made a few minutes after the Big Bang. And I'm going to talk about the first metals, carbon, oxygen, silicon, and iron, and so forth, that were made by the first stars. So the technique that I'm going to discuss in quite a bit of detail throughout this talk is called absorption line spectroscopy. It's really quite a straightforward technique. The idea is that you have a bright background light source, in this case a quasar, and the quasar's light, we'll observe the quasar's light with our telescope, okay? And just by nothing more than pure chance, there happens to be a cloud of near-pristine gas that lies between us and that background quasar. And so the idea here is that this near-pristine gas might be this cloud, which must have existed sometime in the universe, which contains the metals from the first stars and will eventually form the second generation of stars. So the goal is to try and find these clouds of gas. And this is the technique that we'll be using. So I have a little movie here to show you what this technique is like. First of all, we have a quasar in the background that's shown by this bright dot. And you can see a bunch of gas clouds in this universe. And this is the intergalactic medium. It's mostly ionized, but there are some neutral gas clouds in this intergalactic medium that create a forest of absorption lines, which I'll show in this movie. For now, I want to draw your attention to this spectrum at the bottom, which is a quasar spectrum, which is what we would see if there was no gas along the line of sight. As I start this movie, you'll start to see that absorption features will start appearing on this quasar spectrum, and the quasar spectrum is redshifted as the universe expands. That's why it's moving to the right. So all of these gas clouds are creating these small absorption features. Now we've just passed a galaxy, and this created a great big absorption feature, which you can see around here. Now this is because galaxies contain a huge reservoir of neutral hydrogen gas. And so we've detected that as a strong absorbing system. You may have also noticed that to the right of where all this absorption is, you can see some other absorption lines here, and these are due to metals like carbon and oxygen and silicon. And so by comparing the strengths of these metal absorption lines to this hydrogen absorption line, we can get an idea of what the chemistry is of these systems. So here is an example of real data now. So what I've done is, instead of having a quasar continuum, I've normalized out the quasar continuum. So the quasar emission in the absence of any absorption is shown by this blue dashed line across here at the top of the slide. Now, superimposed on this, you can see a bunch of these small absorption features, and this is due to that low density gas clouds that we saw along the line of sight. You also see this great big absorption feature, which may not be due to a galaxy, it may be. The only thing that this is characterized by is a large column density of neutral hydrogen. So it's just pointing our attention to the fact that this is a large overdensity of neutral gas. That's all it's telling us. And we call that a damped Lyman alpha system because of these damped Lorentzian wings that you might see on the right of the absorption feature. In particular, in this talk, I'm going to focus on the most metal-poor damped Lyman alpha systems. So what you see here is a metallicity distribution function of damped Lyman alpha systems. And this terminology, which is going to appear throughout this talk, this square bracket notation, it's a way that we represent chemical abundances. So in this case, 0 would represent the solar relative abundance of chemical element M relative to H. -1 would be 1/10 of the solar abundance. -2 would be 100th of the solar abundance. -3 is 1,000th of the solar abundance. So we're most interested in trying to find these DLAs, which are in the tail of the metallicity distribution function towards the lowest metallicities. Now, for those of you who may not look at the periodic table of elements very much, this is the periodic table of elements that we can probe with damped Lyman alpha system. So there's a lot of elements that we can't probe. In blue, I'm showing what we could potentially observe with a typical DLA with a future generation of 30-meter telescopes. Now, the future generation of telescopes, just for the most metal-poor DLAs, are shown by the red. And what we can currently have access to are the green shaded elements. And so that's going to be the focus of today's talk, the green shaded elements. Now, I'm going to really impress upon you the utility of these near-pristine gas clouds. Okay, they're extremely rare, but they're like a gold mine, because if you find them, they are still pristine enough that they contain the products that were left over a few minutes after the Big Bang. But not only that, if we find just the right system, we can find gas clouds that have only and purely been enriched by the first generation of stars. Now, as a result, we might be able to study in these systems the transition from the population 3 or metal 3 stars down to population 2 transition, which is when we start forming that low mass generation of stars. Okay, so we can study this pop 3 to pop 2 transition. And also the ultra-faint dwarf galaxies, or the lowest mass galaxies that we currently know about that are in orbit around the Milky Way, they must have formed in a dark matter halo that contained neutral gas, extremely metal poor neutral gas at some earlier times. And so these gas clouds must exist somewhere in the high redshift universe, and it might give us a chance to study the antecedents of these ultra-faint dwarf galaxies 10 billion years in the past. So I think they have a lot of utility in trying to learn some of the properties of this sort of extreme universe. In this first part of the talk, I'm going to discuss Big Bang nucleosynthesis. So just so that we're all on the same page, let me describe some of the key aspects of Big Bang nucleosynthesis. First of all, we can perform a calculation of Big Bang nucleosynthesis in our computers. In order to do so, we need to know a few things, a few ingredients. First, we need to know the expansion rate of the universe. We also need to know the density of baryons. So this is sort of the reactants that are going forward to sort of forge hydrogen nuclei into heavier elements. So we need to know the density of baryons or the reactants. And we also need to know if there's some degeneracy between neutrinos and antineutrinos, or this is otherwise known as a lepton asymmetry. So in the case of the standard model, we tend to assume that the reaction cross-sections that we measure in the laboratory today are the same now as they were a few minutes after the Big Bang. That's not a guarantee, but that's one of the assumptions we make. We also have to assume that general relativity is correct in this regime. In other words, assume that the Friedmann equations accurately describe how the contents of your universe cause it to expand. In the standard model, there are 3 families of neutrino species and no lepton asymmetry, or if any, a very small lepton asymmetry. And so we throw all this information into a computer, and what we have at early times is there's sort of an equilibrium, a nuclear statistical equilibrium between protons and neutrons. But gradually the universe expands, there starts to become a favoring of neutrons and protons combining to form deuterium, which is this sort of red curve, which builds up over time. As the universe expands further, those deuterium nuclei can fuse into helium-3 and into helium-4. And in fact, most of the neutrons in the universe get soaked up into primordial helium, which is shown by this sort of dark green line. Okay, but eventually the universe will expand to the point that these reactions are no longer favorable. So the temperature drops, the density drops, and these reactions are no longer favorable. And so we get these freeze-out abundances, which is the plateau towards high times. And so for a given input parameter, and there is just one single parameter that describes the standard model for Big Bang nucleosynthesis, you can get out these output abundances. So to give you an example in this case, in particular for deuterium, so we've started the simulation off with 3 different values of this parameter eta 10. Eta 10 is basically the baryon to photon ratio. So it's the relative densities of baryons to photons. And what we can see is if we start off with a different ratio of baryons to photons, we end up with different plateau values of the primordial deuterium abundance. So in other words, if we can measure the primordial deuterium abundance, we can then back out what this eta 10 parameter is, which is the single parameter of Big Bang nucleosynthesis. Now, it may not come as a surprise to many of you that if the deuterium to hydrogen ratio is proportional to the baryon to photon ratio, it's also proportional to the baryon density. And so by measuring the primordial deuterium abundance, we can get a bound on the baryon density in the universe. We can also get measurements of cosmological parameters, including the baryon density, through observations of the temperature fluctuations that are imprinted on the cosmic microwave background, as recently recorded in excruciating detail with the Planck satellite. And just to give you an idea of the sensitivity of these cosmological parameters to how the sort of the power spectrum changes. So what we've shown here is sort of it's power as a function of scale, effectively. So it's how much power on a given scale. So wide scales or large scales are shown by low values of L, and small scales are shown by high values of L. What I want to draw your attention to is the baryon density plot, which shows you that the ratio of the heights between the first and second peaks inverts for different baryon densities. So it's the relative heights of this first and second peak that's sensitive to the baryon density primarily, whereas all of the other parameters that are shown here change this power spectrum in different ways. Now, just a moment of clarification. Throughout this talk, I might mention the effective number of neutrino species, which is different from the number of neutrino species. So the standard model has 3 neutrinos. And so the standard model value of the effective number of neutrino species is about 3. It's a bit higher than 3, but I won't go into that detail. So if I now talk about an effective number of neutrino species of 4, it could be that this first case is the case where you do have an actual additional neutrino, one that's not been discovered yet, a sterile neutrino. Or you could equally well have the 3 standard model neutrino species plus some other varying variation of the standard models. In this case, it could be a varying gravitational constant. The point is the effective number of neutrino species is just a way that we characterize non-standard physics. So non-standard expansion rates is all sort of encompassed by the effective number of neutrino species. But this is not the same thing as the number of neutrino species. Okay, so this is kind of a summary slide of everything I've spoken about so far with Big Bang nucleosynthesis. If I just draw your attention to the purple diagonal curves of deuterium in the middle panel here, what this is saying is for different effective number of neutrino species. So the bottom one here is an effective number of neutrino species of 1. The curve up from that is n effective equals 2. The one up from that is n effective equals 3, and so forth. And so if we take the standard model curve and then we have measurement of the deuterium abundance, we track it across to the NF equals 3 curve, we can track it down and get a measurement of omega baryons. The alternative is to get a measurement of omega baryons, say from the CMB, and a measurement of the baryon density, say from Big Bang nucleosynthesis, and see which one of these curves we lie on, because these represent different models of the standard model, deviations from the standard model, I apologize. Okay, so in this way we can combine 2 different cosmological probes and test for non-standard physics. Now, the way we measure the deuterium abundance is by searching for hydrogen and deuterium absorption lines in these near-pristine gas clouds. And so what I'm showing here is the energy levels of hydrogen and deuterium, and the numbers you can see are the principal quantum numbers. And what you can see is that the energy levels of hydrogen are slightly lower than that of deuterium, and that's because deuterium has an additional neutron in the nucleus, and this gives slightly higher energy levels. Okay, so we should see a shift between deuterium absorption lines and hydrogen absorption lines, and that is indeed what we do see. So here's an example of an absorption line spectrum. And here we're showing the transition from principal quantum number 1 to 9. And the hydrogen absorption is this strong absorption indicated by this vertical red dash line. And shifted by about 82 kilometers per second is the neutral deuterium absorption line. So if we compare the strength of this deuterium absorption line to the strength of this hydrogen absorption line, that gives us the relative number of deuterium to hydrogen atoms. So for those of you who may be unfamiliar with absorption lines, there's 2 key benefits of measuring this deuterium abundance in these near-pristine gas clouds. So the first is obvious, it's that it's near-pristine, it's unprocessed material, which is basically left over from the Big Bang. The next thing, which is a little bit subtle, is that if you measure the area under this curve and nothing else, just the area is directly proportional to the number of deuterium atoms. It doesn't depend on the instrument profile, it doesn't depend on the kinematics of your gas cloud or the density or the temperature of the gas cloud, nothing. It's just the area of this absorption line is directly proportional to the number of neutral deuterium atoms. Now, in the case of the bottom slide, when you have these damped absorption line profiles, these sort of broad Lorentzian damped absorption line profiles, again, it doesn't depend on any modeling assumption. It doesn't depend on your instrument. It just depends on the area. So if I can measure this area really well, then that's directly proportional to the square root of the number of hydrogen atoms. So it's very sensitive, and it doesn't depend too much on your model. So it's a very reliable way of measuring this quantity. So here is an example of a damped Lyman alpha system. This is the Lyman alpha absorption line, so it's very strong. This is the transition from principal quantum number 1 to 2. And what you can see is these damped absorption features, which again have allowed us to measure really reliably what the number of hydrogen atoms, neutral hydrogen atoms there are along this sight line. Now, if we now look at the rest of the Lyman series transitions, so this transition at the top left is the transition from principal quantum number 1 to 2. This one is from 1 to 3, that's Lyman beta, still a very strong line. As we go down, we can start to see this deuterium absorption line appearing. So Lyman delta, Lyman epsilon, and we can start to see this deuterium line being resolved from that hydrogen absorption line. As we continue down the Lyman series, we get to Lyman 15, 14, 13, and so forth, and we get these weak absorption features that I was telling you about. So in the case of the top left panel up here, we've got that blue curve that I showed you before, so where you just measure the area and you can get a measure of the total hydrogen column density. And in the bottom left, we have these deuterium absorption lines, and they give us a reliable estimate of the number of neutral deuterium atoms along the line of sight. There's actually additional absorption lines, but I couldn't fit it reasonably on the slide. So we have a huge amount of information, a large number of deuterium, and a large number of hydrogen lines, which has allowed us to measure really precisely the number of deuterium and hydrogen atoms that are in several of these near-pristine gas clouds. So in this slide, I'm showing you 7 systems. These are the 7 best systems that we've been able to find to date. They've all been self-consistently analyzed, and each individual system was analyzed blind, in the sense that all of the analysis was conducted without us revealing to ourselves what the deuterium to hydrogen ratio was in these systems. And once we completed the analysis, we unblinded ourselves. We took that measurement of deuterium to hydrogen and put it in the paper, and nothing was changed thereafter. And what we found is that all of these deuterium measures over a range of metallicity, just to remind you, this square bracket notation, this is 100th of the solar abundance, this is 1,000th of the solar abundance. All of these are in agreement with each other, which tells us that in these systems that are about 100th to 1,000th of solar metallicity, they all exhibit the same deuterium to hydrogen ratio, which we attribute to being the value that was left over from the Big Bang. The value you see on this slide is a weighted mean of all these 7 measures. And if we take these 7 measures and we input it into a calculation of Big Bang nucleosynthesis, we can output what the value is of the baryon density at the time of Big Bang nucleosynthesis. Now, this is a 1% measurement of the deuterium abundance, which is quite astounding. The reason this is inflated to be about a 1.5% measurement of the baryon density is because there's some uncertainty in these nuclear reactions that go into the calculation. And so this error represents not just the uncertainty on the deuterium abundance that we measure, it also accounts for the uncertainty in the calculations. And the thing that is really worth noting here, which I can't emphasize enough, is that the value you get from the CMB is essentially pinpoint exact on the number you get from Big Bang nucleosynthesis. So these are, I think this is a real testament to our current cosmological model. The fact that we have 2 completely independent probes of the baryon density, 2 completely different times, the strategies are totally different, yet they agree to within 1% or better. I find this to be an absolutely outstanding confirmation of the standard model and of our understanding of cosmology at the moment. Okay, so that closes what I wanted to discuss about Big Bang nucleosynthesis. I now wanted to move on to discuss the elements that were made by the first stars. So I remind you about this timeline of events that I mentioned at the start of the talk today. And so again, what we're going to come back to is this cloud of gas, which we believe is in between the explosions of the first stars and the formation of the second generation of stars. Okay, so these gas clouds, which we're trying to find, and we believe we've found a couple of these now, that are near pristine and may still contain the products from the very first generation of stars, and will also allow us to study the formation of the second generation of stars. Now, this is trying to study the first stars has been a long history, and a very successful approach is by using the second stars approach. So in this approach, many groups of people have tried to identify the most iron poor or metal poor stars in our galaxy today, and then compare these to models of nucleosynthesis that we calculate in a computer. So what I'm showing you here is the black points represent the observed abundances of one of the most iron-poor stars we currently know about. And the red triangles connected by lines represents a model calculation of the nucleosynthesis from the first stars. And overall, this provides a very good representation of the chemical abundances in this star. To show you another example of this, in this case, the black data represents a sort of an average or a typical spectrum of an extremely metal-poor star in the halo of our Milky Way galaxy. And I again remind you of this square bracket notation where 0 represents the solar relative abundance, and -5 in this case would represent a third of the solar abundance, and plus 0.5 would be about 3 times the solar abundance. So we can see that basically all of these elements are within about a factor of 2 to 3 from the solar ratio. Okay, so I first wanted to highlight that we can do similar measurements in these metal-poor damped Lyman alpha systems. So first of all, the gray data that you can see in the background of the slide here, this represents the oxygen and the relative oxygen to iron abundance as a function of the iron abundance for stars. Okay, so the gray data comes from stars. The blue data comes from damped Lyman alpha systems. Okay, so the damped Lyman alpha systems have a relatively higher precision than the stars. Oxygen is quite a difficult element to measure in stars, but it's actually relatively straightforward in DLAs. And the real crucial thing I wanted to highlight about this recent work by Louise Welsh, PhD student at Durham University, is that Louise is focused on these sort of lowest metallicities, really probing 1,000th of solar and below, which is quite astounding. And what Louise has found is that there seems to be an inflection, which I mark here as a green arrow to sort of guide your eye. Higher metallicity DLAs all show about the same value of the oxygen to iron ratio. But as soon as you go below 1,000th of solar, we see a sort of a kick up or an inflection where the oxygen seems to be somewhat enhanced over the iron abundances. Okay, this is something that's also been seen in stars in the sense of having enhancements of the lighter atomic number elements, such as oxygen, relative to higher atomic number elements, such as iron. But this is really, I think, the first tentative evidence we've seen in damped Lyman alpha systems. I next want to draw your attention to this point down the bottom. This is the most metal-poor DLA we currently know about. We haven't detected its iron yet, but Louise has a program to go and secure this iron abundance. But if it were consistent with this sort of plateau of damped Lyman alpha systems at higher metallicity, then we expect the iron abundance might be somewhere down around about -3.5. That's our best guess. But if there is this inflection, it may even be somewhat lower iron abundance. We're going to find that out soon. But I now want to talk about this most metal-poor damped Lyman alpha system because I think it's an important discovery. So this is the chemistry. So those of you who are interested in the numbers, here are the chemical elements that we've detected and the limit we've placed on iron at the moment for this system. It's, I think, one of the most carbon-poor objects ever discovered with metals. I think it even is the most carbon-poor object of all stars currently known, maybe with the exception of 1 or 2 stars. So this really is a very pristine system, near-pristine system. And on the right of the slide, what I show is the metallicity distribution functions of 6 ultrafaint dwarf galaxies that are in the halo of the Milky Way. Now, the red line indicates the current limit on the iron abundance that we've measured from the data, but the expected iron abundance is probably somewhere down around here, which is indicated by the blue line. So we'll find this out by the end of this year, but I think the key point here is that this cloud of gas has an iron abundance which is consistent with the most metal-poor stars in ultrafaint dwarf galaxies. And we're now talking about this gas cloud, which is near pristine and has chemistry that is representative potentially of the ultra-faint dwarf galaxies. So I think this is tentative evidence that we may be starting to probe down to the sort of regime where the lowest mass galaxies might form. One of the other things that we can learn from these near pristine systems is this sort of transition from a population 3, massive generation of population 3 stars, the first stars, to a second generation of metal poor stars. And this has sort of been described in the literature as this transition discriminant, which is seen on the left here. The uncertainty in this discriminant is sort of given by the shaded band. And the idea is that this transition discriminant is assuming that carbon and oxygen fine structure lines are the things that drive the gas cooling from a predominantly high mass generation of stars to a low mass generation of stars. And this green point represents the most metal poor system that I just described in the previous slide. And what we find is it's just past that transition discriminant. So if fine structure cooling is the dominant mechanism that drives the transition from the first stars to the second stars, then this green system may actually be not yet a galaxy at all. It may just be a gas cloud that's neutral and is on the cusp of forming a second generation of stars. So I think this environment is very exciting. And if you were to go anywhere in the universe to look for the first stars, I think this is probably about the best field of view you could potentially look for the first generation of stars in and around this near pristine environment. Okay, so I think now we need to discuss how we can interpret these metal poor DLAs, because it's not necessarily clear what their source of enrichment is, or how they came to be at redshift 3 or thereabouts to have these sort of near pristine compositions. And so this work that I'm going to describe is being led by Louise Welsh, a PhD student at Durham University. She'll be soon moving to Milan on a postdoctoral position at Milan. And so what I'm going to do is just draw this cartoon idea of Louise's model. And so in this case, we have 3 mini halos. And the yellow stars that you can see here are going to be representative of the first stars in each of these mini halos that sort of don't talk to each other at this point. Okay, so this is one mini halo that contains 3 massive first stars, a completely independent mini halo that has 5 massive stars, and another independent mini halo which has 1 massive star. So the key thing to point out here is that each mini halo formed a different number of first stars. And this is because when you're in this sort of low count regime of first stars, the IMF, or the initial mass function, is stochastically sampled. So you don't get an even distribution of the full initial mass function. You may only sample 1 or a few stars from this IMF. And it's important that we account for this in understanding the chemistry of these systems. So we're going to assume that these mini halos all evolve separately. They all explode as type 2 supernovae or some kind of supernovae. You have to excuse the poor animations. They then disperse their metals into these 3 gas clouds. So these gas clouds are now uniformly enriched by the metals that were produced by these supernovae. And later in the universe, these clouds might actually combine and mix further. And it's at this point that we observe this gas cloud in absorption against a bright quasar. Okay, so that's the sort of model we have to factor in when we're thinking about chemistry. It's not just one model of the first stars and compare that to one measurement of chemistry. We might have to consider several models of stellar nucleosynthesis that go into a single measurement. Okay, and so that's the model that Louise has generated. So what we have here is, if you see this equation on the top of the slide, this is the number of stars that are produced for a given IMF. So we're integrating the IMF between some minimum mass up to some maximum mass. And this sort of inner part of the integrand is just representing what the initial mass function might look like. And we've expressed this as a power law of slope alpha. Okay, so an alpha of 2.35 roughly corresponds to the salpeter case. Okay, so the key parameters here are the minimum mass, the maximum mass, the spectral slope, the number of stars that go into enriching this generation, and that number of stars that we have sets what this value of K is. Okay. So I'm now going to start this little animation, and this should explain why we can make this measurement that we're trying to make. Okay, so the measurement we're trying to make is we're trying to estimate the number of massive first stars that have contributed their enrichment to these metal poor DLAs. Okay, we're actually trying to get a number of stars. And the reason we can do this is because if we look at 10 DLAs, it may be that one of those DLAs was enriched by 5 stars, whereas another DLA was enriched with 5 stars, but there are different mass range of those stars, okay? Said differently, imagine all DLAs were enriched by just one massive first star. One of those DLAs might be a 20 solar mass star, one might be a 30 solar mass star, and those both have different chemistry and different chemical abundances. So when we look at those DLAs, we can see that there's sort of a dispersion, or we can see they're different. We can see the chemistry is different, which means that they're different stars. Now, if all DLAs received an IMF weighted abundance, then all DLAs should have exactly the same, say, carbon to oxygen ratio. And so that's what's shown in this bottom panel here. Okay, so in this case, we have one star that's enriched every single DLA. And one of those stars might have been a 20 solar mass star, which gave this carbon to oxygen ratio. One star may have been 40 solar masses, and that gave this carbon to oxygen ratio. Okay, so if I start this animation, you can see that as DLAs get enriched by more and more stars, the shape of this distribution becomes gradually more peaked. Okay, until the limiting case where you get an infinite number of stars, and that means your IMF is really well sampled, and this becomes a delta function. So the goal is to try and measure the width of this distribution. It's basically the scatter, the intrinsic scatter of the carbon to oxygen ratio. And this should tell us how many stars enrich the most metal poor DLAs. So Louise has done this a few years ago. What she found was we only had a small sample of metal poor DLAs, but the peak of these distributions was roughly consistent with salpeter. We found that they're predominantly enriched by very few stars. We found interesting evidence that there may be a maximum mass of around 25 to 30 solar masses, which may not be able to explode as type 2 supernovae. And this is being seen quite commonly now, that people are finding stars in this mass range, which then disappear in later exposures, later imaging exposures, and they've sort of gone off without a supernova explosion. They're like direct collapse black holes. So this may be quite an interesting, observation that's being picked up in the damp lime alpha systems. So something else that we can do is measure the stellar mass. We can estimate the stellar mass. I'm not going to go through the details, but basically we have an inference on the number of massive stars. And if we then extrapolate this to assuming some IMF, we extrapolate this to integrate over the whole IMF, we can estimate for a given M min what the stellar mass of this gas cloud might be. And we get values that are in sort of a few thousand solar masses, which is sort of consistent with these ultra-faint dwarf galaxies, which is potentially very interesting. Okay, this same analysis that I've just talked about with damp lime and alpha systems can also be applied in stars, metal poor stars. One thing I want to point out here, so Louise has used 4 different samples. Okay, the biggest sample is the rotary sample, which is sort of these sort of purple region up here in the magnesium to iron ratio. The problem is that this is well known. There's sort of an offset between those and other measurements. So I'm going to present the rest of this talk with the 2 different measurements. So shown by this sort of legend down the bottom right. The purple is the one, sort of our fiducial one, where we don't include this rotary sample because they're offset. We find that These measurements are again consistent with the Salpeter distribution. The number of stars that we estimate has a peak of around 5. So we think metal poor stars, the most metal poor stars may have been enriched by about 5 massive stars is our best guess, but this is still quite a large dispersion at this point. And what I wanted to point out is some work by Tillman-Hartwig back in 2019, who reached very similar conclusions. So Tillman used a slightly different model. The goal of Tillman's work was to assess whether the most metal poor stars were enriched by a single star, a single first star, which he's called mono-enrichment, or whether they have been enriched by multiple stars, which he called multi-enrichment. Okay, so it's slightly different, but complementary to what we have done. So in this case, Louise has estimated or put a constraint on the actual number of stars that may have enriched these systems from a statistical viewpoint, whereas Tillman is looking at this from a sort of a binary, is it mono or multi-enriched? Okay, so that brings sort of the end of the main science aspects that I wanted to talk about today. I wanted to give you now a sense of why this research is only going to flourish in the coming years. Okay, and to do that, I'm showing you this is the quasar luminosity function. So there's very few faint quasars, but there's lots of bright quasars is the main point. So I've shaded a region here of the quasars that we currently have access to with the 8 to 10 meter class telescopes. Now, if we now move to the next generation of 30 meter class telescopes, we have access to this many quasars. So this may not seem all that impressive to you because it's just a shaded line over a function. But if we now look at this, what this looks like on the sky, so this is just 10 degrees by 10 degrees on the sky. And if we were to look at this 10 degrees by 10 degrees patch of the sky with our current telescopes, we might find about 8 quasars, which we can observe with the current generation of telescope facilities. Now, in this same patch of sky, we can now, with the future generation of telescopes, observe this many quasars. So it really is a huge, huge improvement because of that the steepness of that quasar luminosity function. And if you increase the number of quasars, you increase the number of sight lines by about a factor of 100, the number of metal poor DLAs that you could in principle observed. So in this case, we're talking about a factor of 100 times the sample that we've currently got. So 100 times as many deuterium measurements, or 100 times as many near-pristine delay samples that we could study with the first generation of stars. So I think this is a really exciting and hugely promising field for future research. And the best part is we currently know the damped Lyman alpha systems that we have to go after, even from SDSS, and we're going to have excess from Foremost, for example, in the future, and Weave. So there's going to be a lot of damped Lyman alpha systems that we all know about and can follow up quite readily with future generations of telescopes. So I've just hit the 45-minute mark. So let me just close by giving a couple of summary points that I discussed today. So first of all, I discussed how these near-pristine gas clouds allow us to pin down cosmological parameters, including the baryon density and the effective number of neutrino species really well. And currently we see good agreement between BBN, C, and B. I reported the discovery of the most metal poor damped Lyman alpha system currently known, and the chemistry of this system appears to be consistent with what we see in the lowest mass galaxies in orbit around the Milky Way. So this is exciting because we may be able to study the antecedents of damped Lyman alpha systems 10 billion years in the past, antecedents of the ultrafaint dwarf galaxies 10 billion years in the past. I also mentioned that this DLA has crossed the threshold that we believe may be the transition from population 3 to population 2 star formation, if fine structure cooling is the dominant thrust that drives this transition. And so these 3 points that I mentioned, it could mean that this DLA is a precursor of a first galaxy. It may not yet be a galaxy. It could just be a cloud of gas on the cusp of star formation that may create the second generation of stars. And this may be one of the antecedents of the ultrafaint dwarf galaxy population. Louise is just about to submit a paper Louise Welsh, on a possible inflection of the oxygen to iron ratio at the lowest metallicities, and this would be a signpost of metal-free star formation. So this is a really exciting result. Finally, Louise has also developed a model that allows us to infer the number of stars that may have enriched the most metal-poor DLAs and stars. And so with that, I'll leave you with the main conclusion for the future, which I think this field of metal-poor DLAs is going to flourish. And thank you for your attention throughout the talk.
Thank you so much, Ryan. That's quite an eye-opening insight to Big Bang nucleosynthesis, but also maybe the end of the Dark Ages, or even the Dark Ages itself. So I'm sure there's lots of questions. Today, Ryan won't be able to stay on, so we'll have to get through the important questions before the top of the hour. So I think the first hand I saw was from Francesco.
Yeah, thanks. Thanks, Ryan, for this amazingly clear talk.
Thank you.
I have a couple of questions, but I think that I can postpone the second if there is time. So my question is, on the stochastical chemical enrichment that you showed us, how much is it dependent on the IMF that you assume? Because, I mean, if it really is sensitive to it, you could do the other way around. You can constrain the IMF with your analysis, right? You mentioned that the enrichment is compatible with the salpeter distribution, which could be very peculiar. Then you would be able to to constrain the IMF very precisely and still find a salpeter distribution on very low mass stars, for instance. So can you elaborate on that?
Yeah, that's a really good question. Let me go back a little bit. Yeah, so we have assumed a power law version of the IMF. This could be changed, of course, but yeah, at the moment, all we have is the flexibility in the IMF is only in this sort of this alpha parameter. It's not particularly sensitive, as you might have seen. It's consistent with salpeter, but it is still a very broad distribution. So one could try log normal or Gaussian IMF or so forth. The reason we chose this is because it sort of has sensitivity to favoring low mass or high mass, and by also allowing this sort of minimum and maximum masses, it sort of can constrain it and sort of tie it into a different mass range. So, so yeah, I don't think the results are hugely sensitive to the IMF chosen, just because of the flexibility that we've allowed with the IMF. Sort of, it can favor lower mass or higher mass stars in general. But yeah, it's a good point. I suspect, to elaborate, I suspect that the key uncertainty here is actually the nucleosynthesis yields. I think that's probably going to drive things in the future. It'd be good to get improved understanding of what the nucleosynthetic yields are. I think that will help the approach significantly. But yeah, that's a very good question.
Depending on the minimum mass that you consider, if you take, for instance, a Krupa or something like that, I guess that your result might change a lot. I don't know. I mean,
so this is only massive stars. So the
sure.
The
minimum, the number, yeah, sure.
Yeah. So
okay, thanks a lot.
Yeah, no problems.
Diederik?
Yeah, fantastic talk, Ryan. Thank you so much. I have a bit of a naive question, but potentially also quite blue skies. So I'm very struck by the constraints that you get on the enriching stellar populations, relatively few massive stars, which probably means something like, a few hundred to maybe a few thousand solar masses, which is quite low. One thing that's really interesting there is there are no globular clusters really with metallicities below -2.5. What do you think are the possibilities going forward to the big telescopes that are coming up to actually observe the enriching stellar populations? Because I think that sounds like it's really an end-to-end understanding of how those DLAs are being enriched at first and so on. Is there any chance we might be able to observe those populations directly and get their demographics as well?
Yes, that's a really good question. If you were to put an ultrafine dwarf galaxy, say, at redshift 3, the visual magnitude would be about 42. So I think it's still going to be inaccessible even with the future generation of telescopes. One possibility is that you might be able to survey their environments, but again, it's not giving you that sort of clinching information on sort of star counts as such.
Right. Even with lensing, you think it would be problematic?
I mean, yeah, it depends what sort of magnifications you get. If we assume sort of an extreme magnification of like 10, I guess is probably reasonable. Then we're still only talking about high 30s in terms of the magnitude. So I think it's still going to be probably hit by other systematics and maybe even crowding at that point along the line of sight. So yeah, I think it'll be very challenging. I never say something's impossible though. So
for the time being, your only hope.
Yeah, I mean, look, I think there's still a chance. I think that and Louise is kind of leading this effort of trying to find metal poor DLAs. We're trying to find an example of a completely pristine DLA that might be sort of a signpost of there may be first stars in that environment. Because if you find a completely pristine gas cloud to the best of your detection limits and it's neutral, there's a good chance that it may be favorable that it would form a first generation of stars or massive stars. And in that case, we're now talking about something that may well be detectable. You may be able to observe 100 solar mass star, for example. So, I don't think it's out of the question. But yeah, we may be able to detect the massive stars, but not the low mass stars to get the total stellar mass.
Yeah. Cool. Thank you.
No, thank you.
Okay, Andres, Just.
Yes, thank you very much. It was very interesting results. So I have a question to this break point of the oxygen abundance at ion abundance -3. Can you say a few words about the meaning of that, if that really exists? What does it mean for evolution of POP3 stars or whatever?
Yeah, sure. So there's sort of, if this sort of inflection does occur, then there are sort of three ways in which I can think about which could explain this inflection. One is that higher oxygen to ion ratio tends to be produced by more massive stars. Okay, so if I draw on a plot here, if I change this axis to be 10 solar masses, 20 solar masses, 30, 40, 50, and so forth, then the oxygen to ion ratio goes something like this, okay? So in other words, high oxygen to ion ratios are produced by more massive stars. So that's one possibility. It could be just a more massive population of stars has contributed to the enrichment of these systems. Another possibility is that the IMF is different. So you could have the same, you could integrate over 10 to 100 solar masses, but if your IMF for massive stars is sort of tilted to favor more massive stars, this could also be realized as an increase in the oxygen to ion ratio, okay? It's basically the only way you can produce this is by getting more massive stars to produce more oxygen to ion. And so the way you can do that is to sort of cut off your low mass end, or you can tilt your IMF to get more massive stars contributing more. The final possibility, which is also interesting, is that when you have an explosion of a first star, it may be that for the first stars, more of the ion gets locked up in the core of the first star when it explodes. So in other words, the outermost layers can get ejected, but in the center, in the core of the star, that tends to collapse. And so you produce sort of low energy supernova explosions, which can then produce a high oxygen to ion ratio. And so all three things that I've mentioned that could explain this are all signatures of the first stars.
Yeah,
because,
okay, I understand. So that means the third possibility would favor this kink at a given metallicity -3, yeah? I mean,
yes.
this -3 is given by how much is mixed. So it to get a well-defined value, yeah?
Yep, I would agree with that, absolutely.
Which would be this third possibility. Okay, thank you very much.
Yes, thank you very much.
Okay, we just have time for two fairly quick questions at the end. So Hendrik Links, please.
Okay, Andreas was before me, but I just put it out there. So you alluded to the midterm future of the observations with the 30-meter class telescopes, but what about the James Webb telescope? So it was always sold as the machine that will give us the first stars. Do you see some potential?
Absolutely, yes. So yeah, I think to this point, I think a lot of people are focusing on sort of the really high redshift 10 and so forth, galaxies. I'm personally not convinced that we're going to detect a bona fide metal-free population of stars at redshift 10. I think our chances might be a lot better if you were to sort of come lower in redshift. Of course, at this point, lower redshift, you've got less chance of finding a pristine gas cloud. But I think the combination of increasing the number of metal poor DLAs by about a factor of 100, I think it's only a matter of time before we discover an absolutely pristine cloud of neutral gas. And I would think that's your best place to look for in anywhere in the universe to find a metal-free star that might be producing an H2 region, for instance, which you would then target with something like JWST. So it's like kind of the environment of that near pristine environment. It basically would point us to a region of a relatively unevolved region of the universe, which has largely remained pristine. And so I think that is kind of one of the sort of high tier goals of Louise's work, is to try and find and discover an absolutely pristine neutral cloud of gas, which may be on the cusp of star formation. So yeah, I think JWST is going to be pivotal if we can find that sort of big result of an absolutely pristine gas cloud. And of course, near pristine, absolutely pristine gas clouds exist. People know about these, about 3 gas clouds that I currently know of that are like 1/10,000th or 1/30,000th of solar or below, but these are all relatively ionized regions. So no one's found a mostly neutral region. So that's a key goal.
Okay.
Okay.
I should also say I can stay for a couple more minutes afterwards if there are some burning questions, but if people have to leave to go to other meetings, then by all means leave.
I think, yeah, thank you very much, Ryan. You're a victim of your own great talk here. There's so much interest, maybe 1 or 2 questions. I'll just finish the main session with Andreas Troutner.
Yeah, thanks also for this really nice talk. So this should be quick because I feel this is a naive and uninformed question. So to the D2H you measure from this what you call near pristine cloud. So my impression was that these are already enriched by say first generation stars. So why does the D2H not change in this process? Why do you expect this to be the primordial value?
Yeah, this is a very good question. The reason is that a very small percentage of the total gas actually gets processed through stars in these near pristine environments. So you can actually do a calculation to check this. But yeah, so it's about 1 in a million hydrogen atoms or deuterium atoms will pass through a star in one of these sort of near pristine environments, about 1 in a million. So it means that our uncertainties are good to within about a millionth. And when you talk about 100th of solar metallicity, we're talking about 100,000th of every deuterium atoms or thereabouts has passed through a star. And the only thing that can affect this ratio is the burning of deuterium. So as soon as deuterium goes through a star, it gets converted to helium-3 and you don't see it anymore. And so that's the only thing that you're missing. And yeah, chemical evolution models basically tell us that at these metallicities, 100th of solar or below, then you're basically observing the primordial value. To give you another benchmark, in the Milky Way, about half of the hydrogen atoms in the Milky Way have never been through a star. So it's still, even something as enriched as the Milky Way, it's still quite a lot of material that has basically just sat around since the Big Bang and never done anything exciting with its life. So yeah.
Yeah, thanks.
Thanks.
Okay, well, thank you. Before we thank Ryan at the end of the formal meeting, let me just share the screen to advertise next week's colloquium. So I just put this up. And so we're going to go actually back to the local universe, but also back to frontline new discovery type observations, where we'll be looking at the very highest energy photons ever measured by mankind with this new revolutionary detector array. And we'll have the leader of this project, Zen Chao, here to talk about that next week. So please join in if you want to see these discoveries. So now I will ask everybody to open their microphones and open their videos, and let's thank Ryan for this stupendously interesting talk, and we wish Ryan every success in the future to keep pushing this frontier on. Thank you very much, Ryan.